Ladies and gentlemen, good afternoon. Welcome to the SAM Society. My name is Lia Genovese and I'm a member of the lecture committee. Welcome to all of you. This afternoon's presentation will touch a chord with everybody in this room. Memories of the 28th of March earthquake that struck parts of Myanmar and Thailand are still fresh in our minds, more so in the minds of some students from Mandalay who are here today. They are enrolled in the course taught by Dr. Virdis, our speaker today, so welcome to all of you. Tonight's speaker, Dr. Salvatore Virdis, is an associate professor at the Asian Institute of Technology, AIT, in Thailand, with over 20 years of experience in environmental, geoinformation, and Earth observation science. He has authored dozens of peer-reviewed publications and frequently presents at international scientific forums. Now, you're wondering why we have this unusual opening slide here. I think for the benefit of those of us who only have a basic familiarity with the topic, Dr. Virdis has very kindly put together a glossary of technical terms. So feel free to download this on your smartphone, but also we have a number of printed copies. So if you would rather have a printed copy, please let us know and we will bring it to you. Dr. Virdis will ease us into his presentation by going through the glossary. I have been at pains to say, please, Salvatore, make it easy for us, and I know he will. So that is the QR code on the screen. Ajahn Salvatore's presentation will last around 45 minutes and will be followed by a Q&A. Before concluding this introduction, I would like to say that the SAM Society offers a wide array of cultural events, including lectures, study trips, and musical events. Advance notice for these events is provided on their website, thesiamsociety.org. Ladies and gentlemen, please welcome Dr. Salvatore Virdis.
You can hear me, okay. Good afternoon, everyone, and good afternoon, Professor Lia, and thank you for this very nice introduction. Next. Okay, my name is Salvatore. I am Associate Professor at the Asian Institute of Technology. It's a postgraduate institute in the north side of Bangkok, in Pathum Thani, nearby Thammasat Hospital. I am here today to talk about what geospatial tools and what remote sensing can do to support seismic sciences and to support the understanding of earthquakes. I am a professor, I'm a professor at the university, and I'm used to deliver scientific speech with a lot of technical terminologies and jargon. The mandate given from Professor Lia was keep it simple. But you have to understand, you know, we are from our small offices, and then it will be difficult sometimes, but I will do my best to make it simple. This is my journey in my life. I come from a very small island here in the Mediterranean, in the central Mediterranean Sea, and I've been working in North Africa for a while. Then I moved to Vietnam, Malaysia, and now we are based, me and my family, in Thailand since almost 9 years. And I've been working with remote sensing, geospatial tools. I am basically, as a background, a geologist. So I used to work with seismic topics before leaving Italy. Now I'm dealing with the climate change impact assessment here in Southeast Asia. So today's presentation, we try to answer or to help you to answer four basic questions. Why earthquakes generate and where and how? This because we would like to understand what has happened in Myanmar. For many, the earthquake that happened in Myanmar was a surprise. But we will see soon that that event in Myanmar and the consequences in Bangkok should not be a surprise. But this should be something that can happen, and can happen even in the lifespan of every of us. And then we come to the topic, the main topic of this presentation, to understand what remote sensing can do and how remote sensing can support scientists to better understand earthquake, not only for the sake of understanding earthquake, but to prepare responses to the crisis. And then I will show some of the exercises that we did at AIT, that I did personally or I did with my students. So I wanted to start with this very nice infographic that I found a few days after in BBC. It's an excellent graphic that in an easy way explain many important concepts linked to earthquakes. It provides arrows, that means something, introduce the tectonic reasons on the Myanmar event, the location. There are some technicalities like plates, friction. Now let's see in easy term, I hope, what do they mean and why they're important to understand this event in Myanmar. So everything raised here because our planet is alive. Our planet is not a static element. It's moving, and everything basically related to earthquakes origins in the asthenosphere that we have to think as an inner part of the planet that is liquid or semi-liquid. And it is very hot, and it is like a boiling volume of melted rocks that have a convectional movement. And these convectional movements, they trigger the movement of the cooler external part of the globe. So everything is born here. We have lavas that goes outside and they cool, and the movement beneath, they let this plate moves, okay? So the movement of the plate is the first thing that we have to understand to understand what is the origin of earthquakes. We have basically three types of situation that can happen. We have part of the lithosphere that they move away in certain areas of the globe. Some other part of these plates, then they collide, so they collide together. And some areas between plates, that they strike each other. So these are the three main regions that we have to look at when we try to observe earthquakes. Because as every of these type of movement trigger specific type of earthquakes. And Myanmar earthquake, we will see soon, can be framed in one of these tectonic settings. So the globe can be seen as a puzzle, as a jiggle of plates that are moving together, okay? And to ease your understanding, I put some arrows. So when you see blue arrows, these plates are pulling apart. They are generating new lithosphere, basically is oceanic lithospheres. And when you see the red arrows, plates are colliding using usually in colliding areas you have generation of mountains or volcanic activities. All of these regions are place for earthquakes with different typologies. But we have to have a look for today in very specific areas where the plates, instead of colliding or pulling apart, they strike each other. Okay, so they have horizontal movement to each other. These are, just for your understanding, this is the circle of fire. And if you notice from the New Zealand, Philippines, Japan, Aleutian Island, California here, Mexico, Chile, these are regions where very, very strong earthquakes happen in exactly those colliding zones. What happened in a small scale is that we have faulting. So whenever the stress is very high, what happened is that the stress can be higher than the capacity of the rock to sustain stress. And then it breaks. And then when it breaks, earthquakes happen. And these happen through different geometries according to those movements that I was explaining before. So if we have extensional system, we have so-called normal faults, where an hanging wall will subside, if we take the reference, the foot wall, or we can have a reverse fault if we are in colliding zones, or we have strike slip faults, okay? When we talk about Myanmar events, we are in this setting, and we are going to understand soon with some figures and graphics. So let's now focus on the Myanmar case. In Myanmar, we had this event on 28th of March, 1 p.m., more or less around 1 p.m. And I just checked a few days ago in the Relief Web service. We count more than 3,700 deaths, almost 3,800. These are formal and official figures. More than 5,000 injuries. 88 died here in Bangkok, and we know because, why. And of course, a lot of damage, a lot of disruption in activities, and with the value of the damage that is more on almost reaches $2 billion. The focus of this earthquake, the epicenter, which is the surface manifestation of the rupture of the, let's say, of the lithosphere, happens in Mandalay. It's the second city of Myanmar with more than 1 million of inhabitants. And of course, all of us felt the earthquake here in Bangkok. I remember very well, and I guess that everyone has his own image of what has happened here in Bangkok. So I will show you a little bit now what has happened there in terms of, let's say, tectonic and geologic aspect, just to understand the very basics. And I will show you what we can do with remote sensing, how we can use remote sensing, how we can use geospatial science to better understand and to drive a better understanding of earthquakes. Since the early beginning of remote sensing, these techniques, they have helped significantly the understanding of earthquakes. So I will show you how. First of all, remember, I introduced plate tectonics in a very simple way. We are focusing now in a very important region around the globe, where the Indian plate, which is at the left of this image, is colliding with the Eurasian plate. And this has a main consequence of orogenic formation of the Himalaya. So Himalaya is generated because of this collision. And this plate, they move. They are not static elements. They move with an impressive speed of 50 millimeters per year. I said impressive because 50 millimeters per year is extremely high velocity. And as a consequence, the Eurasian plate is receiving this big push from the Indian plate, let's say, and is moving itself towards southeast, okay, with a little bit lower velocity of some tens of millimeters per year. What happened in between? In between, something is happening, and we have to focus in this area. We have a much lower velocities. And we have what is called Sunda block and what is called Burma block that are squeezed in between. And this specific location for these blocks let something happen in so-called Sagaing fault. That if you read a little bit the news during the earthquake, you heard this name, Sagaing fault. Sagaing is a location nearby Mandalay. Okay? So what we have to know is Indian plate is moving very fast, Eurasian plate is moving towards southeast a little bit slower, and something is happening here. So, first of all, how we know the velocity of the plates? We know because we can measure through GPS or through GNSS. These are systems, satellite-based systems, that measure the position of a point in time. So if you know the position of a point every day, then you can track how this point is moving. So we usually do this by monumenting antennas and instruments and making continuous monitoring of the position of this antenna in time. This can be, these are permanent stations that record the positions for many, many, many years. Of course, there is the need of maintenance. And every point on the left of this image is as a station. And then, by, of course, not easy to, probably to tell, but not easy to do, we can calculate the velocity of each station. So we know the position of each station in time, and then we can calculate the velocity, what I told you before, those 40 millimeters per year. And here, if you focus on those arrows, this is the direction of the plate in that specific point, and the length of the arrow is proportional to the speed. So the longer is the arrow, and the higher is the speed. And you can see that here we have higher speed than here. So now you can understand the previous slide. Okay? And you can see that everything is moving northward and southward. And now we arrive to Myanmar. Here with this very nice infographic from USGS, from the United States Geological Survey, we can observe what has happened since the beginning of the last century. And here in the y-axis we have the strength of the earthquakes, and here in the map we have the location of those earthquakes. So we learn first thing, we have many earthquakes. So what has happened in Myanmar is normal. It's a very normal activity, and it's normal to have very strong earthquakes, more than 6, and most of the time even more than 7, okay? And second lesson learned, these earthquakes are strong. They are strong because they are shallow, so they happen very shallow. In the collision areas, here in subduction zone, earthquakes are very deep. They can be 50 kilometers deep. They can be 60 kilometers deep. We still have very strong earthquakes in this area. This on the Andaman Sea, we know all the earthquake that generates the tsunami. It was in a very similar region, transformed region. And when this has happened, large volumes of water have been bounced up, and this has generated the tsunami. But this was just a small open and close bracket. We focus here. So around this area, many earthquakes, okay? And these are the main earthquakes, and even recently we had very, very strong earthquakes in the last 60 or 70 years. All of them are in the Sagaing, distributed over the Sagaing fault, okay? Now, very interesting for those that are following this narrative is in the last 100 years, many of these earthquakes has happened in the north part, very strong. And some other they have happened in the south part. Between the north and the south, we are talking about a distance of more than 600 kilometers, 700 kilometers. The Sagaing fault is long 1,000 kilometers. And by reading the scientific literature, we can see that we have a very high density of earthquakes in the north, those beach balls, red colored in the north part, and in the south. Those that are blue and purple, they are linked to the subduction activity, not really related to the Sagaing, but the ones that are in the center are linked to the Sagaing fault. And they are all superficial. What you can observe, and no need to be a scientist, that between the north and the south, there is a big gap. So if we read the historical records of the earthquakes, we can observe that in the last 120 years, nothing has happened in between these two areas. And the last earthquake on 28th of March happened exactly in what scientists called seismic gap. So, was it predictable? No, because predictability means several important concepts. You have to say what, when, and how much. So you have to say in which day, where, and how strong will be your earthquake. And this is really, I mean, with the knowledge and techniques that we have now, this is not possible. But we can say that statistically, the chance to have an earthquake in that area was very high. And exactly at the beginning of the early 2000s, scientists said, we have to pay attention in this area because earthquakes with a magnitude lower than 7 can happen anytime. And this has happened. So once again, I read in many newspapers, in many interviews, and YouTube, many people surprised. And even people caring about their condos, they did not expect something like this. But we have to have a long memory and expect that this can happen in this region of the world. So while in that period we have access to this type of information, in many newspapers we saw that map, colored map, where the color tells us the intensity and the speed of the waves generated by the earthquake. The reddish is the color and the higher is the energy. And then this color migrates to yellow, to green, and to cyan color. The farther we are from the epicenter, and the lower is the intensity of the earthquake. And look, I point here, this cyan color, that if we connect to this cyan color here, it tells very light, very slow waves. It means that the more cyan is the color, and the smaller are the waves, and the intensity of the earthquake is reduced. And we can see that the intensity is very low in the Bangkok area, more than 1,000 kilometers, far away from the epicenter. So we were all here, I guess, majority of us we were around here, but we felt it. And if you see, maybe the lights does not help, the shape of these cyan colors are not rounded here, okay? But they are coming down here up to Bangkok. There is a motivation, okay? I can explain later. So there is a diversion from a round shape, contour lines, up to the south, close to Bangkok. This explains how we feel it. I can say a few words later on. So, scientists, they have interest in understanding and model the fault. Model the fault means giving it a shape, understanding the slip. So how many meters the rocks have slipped, okay? And how many meters and where in this fault. So how it is long, how it is deep, the orientation. This is very important, not for the sake of understanding the fault, but because this can help the scientists to know what could happen next and in which direction, in which location. So scientifically it's interesting to understand what's next, and even after the earthquake, we can plan because we can say where aftershock will likely happen. and if we know where aftershock will likely happen, we can take countermeasure. So by reconstructing this, we can have an idea of what can happen after the quake. This is for, who, like us, they work every day with this type of representation. This is how the fault has been modeled. The color tells us the slip, so how many meters. And the higher is the color towards the purple, and the higher is the number of meters that the Earth has slipped in this surface. Here we are in the north, over there we are in the south. So here we are close to Mandalay, and over there we are close to Naypyidaw, the south of Myanmar. Pay attention to one number, 460 kilometers. This is a huge number. We have to imagine that the two sides of the fault, they have slipped relatively for a ruptured zone that is 460, I will show you, it will be even more, 480, almost 500 kilometers, okay? It's a huge number. The Sagaing fault is top 3 biggest fault in the world. So once again, this type of events should be considered as normal. We should expect such events in this region. And we know the main ruptured zone, okay, so we know this is the Ipoh center, and we can also retrieve the epicenter on the surface. Ipoh is down, epi is up on the surface. Why I'm showing you this? Because to do this modeling, we need, of course, some mathematics, some geophysics. We need to know, we have to have numerical models. We need to have some input information. And here where remote sensing plays a role. Because remote sensing from the top can provide input data to improve the modeling. And it improves a lot. If you check the model, how it was done few hours and few days after, and now is a completely different model, because now with the availability of images, we can refine the results of the fault modeling. So we know now many things about the fault, the movement, the geometry, the aspect, all the geological and geophysical aspect. So it's not a pure, as I said before, it's not a pure scientific exercise. This helps to understand even what's next, okay? So GPS and satellite are used as an optional, but optional doesn't mean not important, because these models, they work without remote sensing. They just need geological and geophysical information. But remote sensing and GPS help to constrain the model. So the model have to fit what are the observation registered, monitored, assessed by satellites. As I said before, these help also to plan aftershock plans from a wide spectrum point of view. So now we come to remote sensing. We have understood the origin of the earthquakes, why they happen, where they happen, why they can be strong in certain areas or less strong in other areas. In this case, they were very shallow, okay, so very strong. Let's see, what is remote sensing? So remote sensing is, as I always say to my student, is sensing remotely. So we want to sense something without being in touch, what we are observing. It means the measure that we do is not in touch with the object we are observing. And we need sensors. So basically behind remote sensing activity, we have sensors. When we take a picture with our mobile phone, we are doing remote sensing, okay? And basically what is on board of satellite is the more complex version of what we have in our mobile phone. So we have a sensor that is sensitive to the electromagnetic energy, and in somehow this electromagnetic energy is captured in form of colors and shapes. And when we talk about remote sensing, we talk about energy, but this energy comes from where? We have two basic typologies of remote sensing systems. One system that record and store the energy that is generated at the level of the sun. It is reflected by the Earth, or generated by the Earth, and then it is reflected to the sensor on board of the satellite. So the satellite stores this information, like we take a picture with our mobile, and then there is a connection, and this image is sent wirelessly on the Earth, and we can use it. Very simple schema. We have another system where the energy is not generated by the sun, but is generated by the sensor itself. So on board of the satellite, we have one sensor that generates a pulse and energy, and then switch and record the energy bounced back by the Earth. So the big difference is the origin of the energy, sun or sensor itself. Okay? This makes the big difference. And now we show you two different applications linked to these two typologies of sensor. When we talk about energy, we are focusing only on a very tiny portion of the electromagnetic spectrum, what we call visible. Okay? Our colors are a portion, very tiny portion of the electromagnetic spectrum. We go to the near infrared and to the microwave. Yes, microwave. Those about the waves that let our oven work, or even our mobile phone work, microwaves. Okay? But a very tiny portion compared to the whole electromagnetic spectrum. The first system with the origin of the electromagnetic energy from the sun works here. The second system, the active one, works here. Okay? Now, let's have a look. What are the main characteristics? With few slides, without any physics, without any formula, you will understand what are the characteristics that we use in remote sensing. First of all, what is an image? An image is visualized for us in terms of colors. But behind colors, to each color is associated a number. And the higher is the number, and the higher is the reflected energy. This is very important for technicians like us. But for you, look, color will be enough. So color will tell us how much energy has been reflected. One point very important, these are numbers. So we treat images as a number, not as a color. Color is the last step for us. So obeying numbers, we use tools like statistics to manage our image. So basically, we do a lot of statistics. Then we show the results in terms of images, in terms of colors. But behind colors, there are numbers. Then another characteristic of remote sensing is the spatial resolution. So it's the smallest element that we can catch, that we can observe through remote sensing. And for many applications, better to have, let's say, unfocused or unclear images. But for majority of the application, we also need high detail, high geometric detail. So we look at the geometry, the shapes, but also we look at the radiometry, the quantity of energy. Both of them will tell us something. Another characteristic about remote sensing is they are very powerful tools. We have only two eyes, but remote sensing systems, they have many eyes. And for each eye, we have one image. So this, how to interpret this set of images? This image is taken on the same day by the same sensor, but with different eyes. How we can easily interpret, if we see change of color, it means we have different type of information. If you see that the color is changing in a certain area of the image, it means we are getting different information, and it's exactly what we do in remote sensing. And then we can observe through a monitor the different images combined together, and we can color it artificially. And we are not in different times, in different days. It's exactly the same area, acquired the same day, but visualized with different color, and this will help us to extract information. This is what we do every day when we do remote sensing. Another characteristic of remote sensing that is peculiar, we observe large, huge areas in one shot. That is not possible when we go in the field. So going in the field is very useful, but through remote sensing, we have access to very, very big areas in one shot. And there is another characteristic in remote sensing that is time. So we can acquire images in time, every 1 day, every 2 days, every 15 days. Okay, it depends on the characteristic of different sensors. And this will allow us to make monitoring. So not only observation one time, but we can observe phenomenon regularly in time. And this allows so-called monitoring. Okay? And this is very important for earthquake application, and you will understand soon. This was the first, remember, the first type that used the sun's energy as a main source of information. Now let's have a look on those called active sensors. And you know, with one word, one type of this active sensor, radar, radio detection and range. So radar works with very basic principle. Radar generates a pulse, and he knows when this pulse travels. It is backscatters to the sensor, and we know when it arrives. So we know the time travel. And the light, we know the speed, so 300 kilometers per second. So we know timing, we know speed, and hence we know the distance. So through active remote sensing, we know the distance between the sensor and the Earth's surface. That's a very important principle, because if in between different acquisition, this distance change, then we can do many, many, many things. We can monitor the relative position sensor Earth. So if the Earth moves during earthquakes, this can be tracked. So let's see now. We know what the earthquakes are, where they are located, how they manifest on the Earth's surface. The Earth's surface can be observed. Let's see how. So let's focus on earthquakes. We have a certain period where we have no strain. Nothing is happening around this area. Then the strains built up. Where this strain comes from, I told you, from the tectonic activity that let the plates move. Okay? So that strain generates. So when the strain generates, blocks are moving relatively. They are, the energy is cumulated. When the stress exceeds the capacity of the rock to bear this stress, the rock breaks. And then when the event happens, the blocks shift and move with the geometry I told you before. Normal, reverse, or strike slip, with three basic geometries. Then once the energy is released and we feel it, as we know, then this cycle starts again. Strain accumulation, stress release as an earthquake. We have foreshocks, and then again. It's a cycle, okay? Can we do something? Yes, of course we can. We can observe the Earth through both methods. I told you before, right? When it's a steady activity, we wait a few days, we observe the same region. When it starts moving, and we start making some measurements, then the event happens, and I observe after. Before and after, something has changed. The relative position Earth satellite has changed, so can be tracked. Even the relative position between blocks has changed, so this can be tracked and can be measured. Now, a small video. Probably you have seen already this video. Of course, we tried before, and it was working very well. I promise, it was working. Wait. No. Did you watch this video before? No. Okay, it will be very interesting because it's the first type of video of this, the first time that this has been captured ever. How? It's not doing, huh? Please help. So this type of video for the first time ever, record the slip of the two blocks. The first time ever. We tested and was working beautifully. Okay, save it and open again. Maybe we go to YouTube, it will be faster. Is it online? Because it is online? Yeah, because if it is not online, it won't run, that's why. Yeah, it should go now. Yes, now it goes. Now probably we run a couple of times. Now is a full speed, around 13 seconds you can check. Just for your reference, have a look at this pole continuously. I will rerun it again. See what happened to the whole block in that side. Start shaking and then boom, is light. For those experts like me, it's amazing. Of course, we are talking about a tragedy. So 6,000 people lost their life. But from a technical perspective, is something unseen before. I will run it with a decreased speed. Wait, I try. Okay. I will reduce the speed, maybe. Cannot. Okay. Full speed again. Still internet. Yeah, too late. It's publicly available on YouTube, so you can watch at home, but okay, run it full speed, and then our guests, they can make this search on YouTube. Full speed again. Okay, at 13, be ready. Focus on the poles, and you can see even the speed, because it's I mean, it's the real speed. Okay, you notice is astonishing. Now, you will see soon. That block is a right strike slip fault. So it means right. What does it mean? If you stand in one block, the second block goes to the right. But not all transform faults are like this. May be left. So you stay in one block, and the other block slip to the left. This is right. Is going to the north. Okay. So that block that slipped is going towards north. I just make a rough calculation. In 1 second, then we measure through remote sensing, this has slipped around 3 meters. So 3 meters in 1 second. Okay, just to give you an idea about the velocity. Okay, and this video is astonishing. Is the first ever. Okay, it's played more than 1 million times. Then we can go ahead. This is the slow version. No, it's full speed. Okay, fine. It's okay. I think it's an internet-related thing. Okay, so next, we can go next. You can search this online. Now, I get in contact with some colleagues in Myanmar through Facebook. I was pretty lucky to get in contact with some of those colleagues. What has happened on the ground? Beside all buildings that collapsed, this is what has happened. This is a pure slip. We can estimate 3-4 meters just from the picture. Just make some relative assessment by looking at the cars. Some other nearby, the very popular bridge now in many shots on the news. Still 2-3 meters of slip. Some other photo on the ground. So we can observe is basically no vertical movement. There is a kind of vertical movement, but is limited, but mainly horizontal movement, okay? So these people in their garden see the other block shifting 3-4 meters, which is impressive. Then, let's see what we can do with the passive one. Let's imagine, I will be quick, because I'm running out of time soon. I told you we have to have a look at the image before, and we can record the same image after. We can observe that after something has changed, so one side of the image has shifted and another side of the image did not shift much. Can we do something? Yes. How? You can superimpose this image to this, and then manually we can track those shifts pixel by pixel. Then you can make visualization like this. On the right side, basically the two images are not moving or slightly moving towards south, but here you can easily see the shift towards the north. So the question is, can we assess this shift? Yes, it is possible because we can track the pixel where it goes. We can do manually, but luckily we have computers, we can do automatically. So this is the basic principle. We take the image before, the image after, we automatically track the shifts. We can render through colors, so colors will tell us the shift. And I told you before, colors, they have numbers, and they will give you the information of how much was the shift. So we know the direction of the shift and how much. And then we can make some technical assessment where here this is the fault, this is how much has shift north and how much has shift south. And then we can release maps like this. This is just a small shot in Mandalay. What is blue is a shift north. What is yellow is a shift south. The darker is the blue, and the darker is the yellow, and the higher is the shift. So very, very big shifts nearby the fault that tend to be lower, far from the fault. Then we can do many things. First of all, we were able to measure the length of the rupture. It's a continuous rupture from the north of Mandalay to the south, to the city of Piu. Talking about 480 kilometers. 480 kilometers. When we move, we usually take the plane. And you have to imagine that video before, a full block without any interruption. Full block moved towards the north this much. How many meters? We can read it here. From 3-4 meters nearby the epicenter up to the south where the shift is limited around 0.1 meter. Okay? This is a profile from the north on the left to the south on the right. Okay? And we can read the shift as the distance from the black line to the top, and also colors. The reddish is the higher the shift. Of course, it's higher nearby the epicenter. This is taken on the left side of the fault, then we can do the same on the right side, so we can map it. So this can be a very beautiful exercise for me as a professor, but this helps scientists to know more about this earthquake. We can do longitudinal transects or cross transect. So we can move left the fault or right the fault, and we can do similar representation. This is typical way of representing results for us, for scientists. Colors still represent the shift. destructive. Now is coming for me the most difficult part, because this is very hard and harsh technique. Students usually, they hate when we talk about these things because it is conceptually a little bit weird. But the concept is I can measure the distance, sensor target. So if my target changes, I can measure this distance. And I can render to very beautiful color shapes, okay? So the concept is if I am able to count these colorful, beautiful colors, I can count how many centimeters this land is moving away the satellite or towards the satellite. And these colors change in different ways. So by counting the colors and how the colors, they are distributed in space, I can make my analysis. So I can count the subsiding events or uplifting events. So I can count how many centimeters is moving the Earth toward the satellite. And I can make very nice maps of what has happened in Myanmar. Here we are still again around Mandalay. These are colorful. For you are not much significant, but for experts like us, we can interpret very well. And automatically, we can determine the shift. This is a vertical shift. Red went towards the satellite, and blue went far from the satellite. So what we have done so far, we have measured the fault, we have measured the movement towards north, and we have measured the vertical movement. All these informations are very important to understand the dynamics of the earthquake, okay? Now another example, a little bit more in developing stage. We can do the same game, so image 1 and image 2 before the earthquake. Then the earthquake happens, and then I take another image after the earthquake, and then I play. I play like cards. I compare the first two images together, and those images with after the earthquake, and I can use a concept of similarity. So if two images are similar, nothing has happened. If two images are different, something has happened. So I do a kind of similarity analysis with some tools, okay? And then I can make maps of similarity. So I can check similarity map before and similarity map after. If the similarity change, something has happened. And I can track what and where. So I can map so-called potential damage area maps, still color, to let them be understood. So the higher is the color, the reddish is the color, and the higher is the likelihood that something has happened somewhere, okay? Just by making similarity analysis. The result is I can track through colors here where something has happened, and I can intervene after the quake. This is the case of the bridge in Mandalay, okay? So, I'm finishing. We can see things from space, and this helps because it's a unique opportunity to have an overview. An overview not only one time, but overview in time. And we have access to archives that are now 60 years old. So I make my studies in Southeast Asia, and I went back even before the American war in this region. So I make my analysis up to the 60s. So this is not possible otherwise. In the specific case, we were able to track ground movement that only models, and in USGS, they make very, very bad prediction just after the quake, because they were not validated by remote sensing. So remote sensing helped scientists to better model the event. We can do damage mapping quickly to guide post-earthquake intervention, okay? Not maybe necessarily accurate, but quick. So we know where to distribute resources. And this can be done through different type of remote sensing. These bad names for the general public, but it means remote sensing has a variety of tools to do this type of studies. And then another very important concept is that we can study the earthquake before, because this can help to understand what is likely to happen. We don't know when exactly, but we can at least know where something can happen. And of course, we can do something after. So this is just the power and the potential that these sensors, now they are, believe me, a little bit bigger than this one. They are not big like a bus anymore. They are small like this, and we have hundreds. Elon Musk is managing one of these systems, okay? He's not the only one, but he's one of the big players. So I hope that my language was easy to be understood. I use very scientific references. The jargon, I understand, might be a bit hard, okay, for first comer, but I did my best to make it as simple as possible. If you want to reach me out, this is my email. If you want to visit us in AIT, all of you, you are welcome. We have a beautiful campus not far from here, 60 kilometers from here. So all of you, you are welcome. And once again, I would like to thank Professor Leah and the Science Society to host this presentation that has been prepared only for you. So I designed this presentation for you today. Thank you very much. Now I think we are in the Q&A session, right?
Thank you, Gian Salvatore, and thank you also for taking mercy on people like myself who are technically challenged. So now I would like to open the event to the floor. So please let us know you wish to ask a question, and we'll bring a mic to you.
I have a question about the consequences for Bangkok. And we are sitting on 30 meters of mud, I guess. Eh? Mm-hmm. And what about the frequency of vibration, and which can happen to the mud in Bangkok, and which could amplify and destroy Bangkok? And I guess the most affected would be the shop houses, but not the high rises, because the high rises, I think, are sitting on piles of 23 meters, but the others have maybe 6 meters or 8 meters, and the vibration and of the frequencies and the consequences of earthquakes in Burma, the size and the depths or something like that.
Yeah.
Can you elaborate on that?
Yes. Okay. First of all, of course, I expect this type of question, and what you are asking is very technical. You use a keyword, frequency, which is exactly the right word. I try to answer. I am a geologist, so I look more at the earth side, and I am not a structural engineer, so I don't build building. But the concept is pretty simple. When an earthquake happens, waves generates, and waves, they have, as you said clearly, different frequencies, or if you like, different wavelengths. And we have many frequencies, and has many wavelengths. And when these wavelengths arrive here, they arrive already attenuated. So you have to think that these waves, they have a very long amplitude and very low frequency, okay? But why this term matters? This term matters because our buildings, they have a natural frequency. They vibrate naturally because every element vibrates. What happened sometime? That when these wavelengths arrive to our building, interact with the natural frequency of this building. And this can generate a phenomenon that probably you already heard in terms of word, resonance. They can vibrate together. And these increase the vibration frequency. And this is not good for buildings because this vibration may generate shear forces, shear fields, and other type of situation where something can be broke. So engineers, they know this principle. They know it very well. And they build structure that are ready to accommodate natural vibration and generated vibrations. Okay, so all the buildings we are living inside, they are built for these type of events. Okay, In the case of Bangkok, Bangkok lies in a very specific setting made of material, of soils that are unconsolidated. It means they are easily separable, okay? This type of sediments, they have a very specific characteristics. They change these frequencies, okay? And this change is made in a way that these frequencies may interfere with the frequencies of the building. So they amplify, even if they are low energetic, low intensity, locally they can be amplified, okay? And this local amplification may damage a structure, may not damage nearby structure, because it's a micro amplification, okay? This could happen, and this has happened in Bangkok, and this will happen in Bangkok, okay? This will always happen, because this is a natural phenomenon, okay? So by the way, anyway, buildings are built. They know, engineers, they know this. So I remember our colleagues, they say buildings are built to stand up. Might be broken, might be, you don't buy that condo, but they have to save life. So they think about this, okay? In my country, in Italy, which is earthquake prone, we have a microzonation. So we have to study lithologies, and we do microzonation, so we know at very high scale what are the amplification effects, and we force the construction of new building to build in a certain way, because we know already that we will have local amplification. That is what you are mentioning. So I hope that I have understood, that I have answered to your question. Yes, please.
Not completely.
Okay.
So, you know, yes, you talk about the principles.
Yeah.
But when would be the big catastrophe happen here? That the electricity mass would fall down on the street and collapse everything, and I think Bangkok is not prepared for a catastrophe like that, because I don't think there are storage of food or medicine or water, and whatever is in buildings stored maybe not accessible, and so that are some practical persons for planning of Bangkok or planning for the catastrophe.
Okay, I can answer in a very probably easy way, a bit harsh. Probably I'm not the right person to answer to this, because I cannot say about Bangkok, because I am living here since, for many years, but I cannot say that I know if we are prepared, if Bangkok is prepared or not. I cannot answer to this question. But I talk with my colleagues, and they say only one building fall down, and causes are probably pretty known. That there are investigations. I don't want to talk about this, but no other buildings fell. So Bangkok is built to keep standing, and is still standing. So we have to be relaxed. Okay, earthquakes happen. You saw before, an earthquake will happen. They want. We have to be relaxed. Okay, don't create panic, right? So even for myself, I am relaxed. we have to be relaxed. Problems will be anyway solved by experts, I hope. Yes, please.
You were talking earlier at the beginning of the talk about these measuring stations and how you measure the distance. Where are they? Are they dotted around the countryside or in academic institutions?
Okay, yeah. Okay, the way how we use GPS for geodesy, okay? These are geodetic studies. Geodesy study the shape of the earth and all these movements. You can do in several ways. So you can do with permanent stations. So you build monuments where you create a big infrastructure where you host an instrument. And this instrument is always on. Always recording the position, uploading somewhere, many servers around the world, okay? and somebody is using those series. These are permanent stations, so built and always working, always on. Then we have semi-permanent stations. So they work for a certain period of time, and then they are dismantled, and then you have just a certain series of information. And then you have non-permanent, so it means the time that you are using for your measurement is very limited, okay? So there are techniques that they study all these type of data to do exactly what you have observed there. So they reconstruct the position in time of those stations. So permanent, what we are talking about those permanent. So they are monumented, I mean, with cement, okay? Big things, special antennas, special instrument to be on always, yeah. It's everywhere around the world, even in Thailand, in Nepal, in Italy, US, everywhere there are this type of stations, always recording. And we as experts, we have access to those data, we download, we have software to process. So it's a regular scientific geodetic activity, yes. It's for me, it's pretty normal, not activity, because I don't do it. I did it in my past when I was in Italy. Now I'm not working with this anymore. But I used to measure earthquakes in L'Aquila, central Italy, with these tools. Yeah.
So in Thailand, where would you likely go to see one of these?
There are in Thailand. I never worked in Thailand, so I cannot tell you where the stations are, but there are. Every country has. More or less dense, of course. If you look at the western side of the world, so US, Europe, Japan, we have extensive networks, extensive and very dense. Almost every city has his own, or more than a station. The density of those stations decrease, but all globe is covered. Otherwise, you know, we cannot have those beautiful maps. And we know a lot about plates now, thanks to GPS and GNSS. Now, I talk about GPS because everybody knows GPS, but it's not the only global positioning system. We have GPS, which is American and military. And we have Galileo, is the European version. Now the Russian one, I don't remember the name. Russian, I don't remember now. Huh? No, has another name. But anyway, there are 3 or even 4, there are even smaller systems. Chinese, they have Baidu now. So now there are more than, and all globally they are called GNSS, okay? And all of them, they monitor the position of points in time and space, okay? I use GPS because GPS we all know, but it's not the only guy now. There are many other systems similar to GPS. But GPS still very relevant. Did I answer to your question? Okay, thanks.
Well, I have a very simple question. You said there are 3 faults.
Yeah.
And Sagaing is one of them.
Yeah.
Where are the other 2? And is Sagaing fault connected with Nepal?
To a simple question, a simple answer, those 3 types of faults are everywhere. Because for the sake of communication, I have to categorize, but they are all linked. So you have to think that there is one main mechanism, and they are, let's say, a lower scale mechanism. Right. So you can find all of them together, but one dominant.
That's right, yeah. But you said there are 3 most dangerous faults in the world.
Yeah, this is,
what are those 2 others?
Usually are linked to those geometries. I mean, you have earthquakes in any kind of geometry. If you have extensive, if you have compressive, or if you have a transfer. This type is transfer, and is very dangerous because it is superficial, 10 kilometers. 10 kilometers is nothing. So it means big blocks, very big stresses. So it means the stress is very high. When it breaks, it is very immediate release of energy and very shallow. So if it is shallow, the energy is released to the surface quickly. That's why it's dangerous. Those with other geometries happen everywhere, can be so dangerous, the same dangerous, but they have more varieties, okay? So transform are more dangerous because are more shallow, let's say like this. But earthquakes are dangerous almost in any kind of geometry, okay? I have to categorize to simplify. You are not satisfied with the answer.
No, I would like to know the other two.
I think you said, Salvatore, that Sagaing was in the top 3. So I think...
the top 2
yes.
big folds.
Yes.
We have the Andaman 1. Andaman is the continuation of this system in the south. And we also have one very big transform fault in Turkey. Okay? Turkey is another place in the world where these earthquakes are extremely strong, 7, 8. And in Turkey, still a Eurasian plate involved. That is, in that case, shifting on the left side. And then we have another big plate coming from the south, linked to the African plates, pushing toward the north. So this is another one. But this Sagaing is very particular because it's a unique fault, very, very long. So 1,200 kilometers. And the ruptured zone here was 500 kilometers, which is, believe me, a huge number, big number. Yeah. Transform area also in California. California is another place where we have a transformed zone. Okay? Yeah.
I would like to ask a question, so please don't laugh at me.
No.
So whenever there is earth movements, major ruptures, has it ever happened that either the longitude shifts, let's say from Myanmar 19 degrees north, goes up to 18 degrees north, or it shifts right away when there is, as you say, this kind of movement? Can it shift either the longitude or the latitude by 1 or 2 degrees or whatever?
Yeah, is exactly what I was saying here. This is a shift. So what you observe here, okay, colors do not help. I didn't realize before, but this side is red. Okay, now the colors mitigate the map. This area is red. If it is red, this is a shift north. How much? 4 meters. 4 meters in 1 second. What does it mean, 4 meters in 1 second? That in Myanmar now, they have to recalculate all their networks. Because all the places around here for a few kilometers, they have changed their position. So a shift north 4 meters, it means today I'm here, and tomorrow I am there. And we are talking about roads, houses, poles, anything as a shift from here up to there, from 1 meter to 5 meters distributed across. A real shift, you see in the video, a real shift. The longitude has changed.
Really? By how many degrees, though?
No, in meters, no, degrees. In meters, you read here. In the south, a shift 1 meter. In the north, 3 meters or 4 meters. This is a real shift. Real. Okay? You can see in the video. You see that thing moving? That was the shift. I hope that you get the feeling. Huh?
So the coordinates have to be
Yes.
rejigged.
Yes, they have to. Because, coming back to the question before, when we monument those stations, for every station we know the average position, okay? So average position is calculated over the years, right? So this average position before the earthquake was this one, and the average position will be over there. How much? 3-4 meters. So you have to update everything again. These are regular geodetic activities of all public agencies. They are dealing with this. And measurements, they are important because everything is based on maps, position, cadastre, properties. Position matters. Yes, please.
My name is Lance Woodruff. I'd just like to clarify with a comment those who might have missed your earlier sidestepping a question about what might happen to Bangkok.
Yeah.
I think most of us in this room know that there is an issue of corruption in construction, and we have evidence of corruption by Thai companies and by Chinese companies. And all of us have the capacity to look at this or that building and wonder whether the engineering statements were not falsified. If a building is built non-standard, it's more liable to fall down. So
Yeah.
I know in your position as the speaker, it's probably not real.
Yeah. You are right. Okay, being a speaker, you need to know. Okay, but anyway, once again, let's please be confident. All buildings, not majority, all buildings are standing, and they have been hit by a very significant earthquake. So this has to help us to be relaxed a little bit. That building is an independent story. And you know, you are talking about this specific case, but majority of buildings are standing. And from structural point of view, I knew informally, but also from the news, only a dozen of big buildings, they have structural issues. What does it mean? That they have damage to the columns that are permanently damaged. Only 12, but are hundreds of multi-stories building in Bangkok. So this has to be an help for us. Majority of other buildings, or they don't have anything, or they have just, decorative damages that we don't like, because we spend money for condos and we don't want to see cracks, right? But it's not a structural damage, okay? So, yeah, we can be angry, I know what you are talking about, but we have to be relaxed. Bangkok is well built to sustain this type of event. That was a single case. Yes, please.
I was here in 1975, I believe it was around November, when we had an earthquake here. Mm-hmm. I was sitting in an office, I think on the 6th or 8th floor on Surasak Road, having coffee with a friend who had invited me to his office, and seeing the coffee cups move across the desk. And then I'm looking out the window and see buildings swaying like bobbers in fishing, going this way and that way. They didn't fall down. They leaned like the Tower of Pisa.
But they must do like this.
Yeah.
They are conceived to do this. They have to sway, because they have to accommodate the forces coming from down. So they have to move.
That.
Yeah. If they don't do this, they might break. If they are too rigid, those sheer movement, they can break it and then fall. So they have to sway. They build to sway. Okay? But again, I'm not a structural guy. Yeah.
Just one last question.
Yeah, please.
Just on the ability to pre-warn or pre-advise, does it make a difference if on the type of earthquake, whether it's something that happened here, which is minimal distance underground, the chance of pre-warning is small? If it's offshore, you get more notice?
When we talk about prediction, it's just a statistical analysis. By looking at the statistics, space and time, because statistics, you should look time-wise statistic and space-wise statistics. So you can analyze, let's say, numbers by time or by space. Then you can say where likely can happen, but you never know exactly where. You never know exactly how strong will it be. So when we talk about prediction, you have to satisfy all these needs. So by what remote sensing or other techniques can help is to understand where the likelihood is higher. The likelihood is higher. It's like the weather. We know the likelihood, but we don't have any certain number. So earthquakes are still like this. Volcanoes are different. Volcanoes can be predicted because for certain reason, we can say what, when, where, and how much. Okay, but earthquakes is different. It's a single point, and we have the knowledge, we have magma. So we have, the type of phenomenon is different, okay? But we know more than before, okay? But still statistically, at the end of the day, if you want to simplify, it's a statistical understanding. Yeah. Prediction, we are still far.
Thank you very much for the lecture. I don't understand much about the scientific explanation. I have two questions. One is you use moment magnitude measurement instead of Richter. Can you give us a short explanation how the comparison of both? And then I have another question. There was a short video about some, I don't know whether he was an architect or an engineer, who explained that there are different quakes and different shakes, and these ones affect different types of building. You have small buildings like houses, you have medium-sized building, and then high-rises. These shakes may, is that true? That there are different shakes or earthquakes that affect different, like this time it affects the high-rises more than the small buildings?
Yeah, the reason why the effect is different is because the characteristic of the building is different. So let's say you might have the same wave arriving to different buildings. Let's say the inner vibrational capacity of a building is different. So the interaction between building and soil gives you different effect. Okay? It's the interaction together that makes the effect different. Okay? It's linked to the size. So the size matters on the vibration capacity of one building. So the smaller and the different is. Okay? So you might have the same wave arriving, but the impact is different because the type of building is different and the vibration capacity of a building is different. Okay? But potentially the amplification effect, okay, depends on the soil, but the effect on the buildings depends on the buildings itself. So who build the buildings have to know the amplification of the soil so that you build on top a building that can sustain this amplification. You understand? And the way how you build a big building or small building, of course, is different. Okay, I don't know whether I have answered, but I'm not structuralist. I'm talking about the principle itself. Okay, about the magnitude. Magnitude measures the energy. What I show you here measure the displacement. That is not the same. Okay, so you might have even no big displacement of meters like this, but you can have shaking because you can have the earth vibrating. Okay, and not moving too much. So this is another chapter. I prepare a few slides, but I didn't show, but I have here. In conference, we prepare backup slides. And I prepare 3 or 4 magnitude slides, and they say, no, this is a crazy thing. Don't talk about magnitude, because it's too complicated. But when you calculate the energy depends on the stiffness of the earth crust, how big is the rupture area, and how big is the slip amount. So you can put these 3 or 4 concepts in number, put into a formula, and then you get how much is the energy released. Okay, so this is how they calculate the magnitude. And the formula is not really pretty to show in a general public talk, but I prepare. So this is the shear modulus that is linked to the rock stiffness. So how stiff is the rock, okay? Rupture area, you can imagine the bigger is the area and the larger is the magnitude, the energy released. And then the slip displacement. Of course, if you let big blocks slipping for huge amount of meters, then the energy that you need to trigger this movement is big, okay? So this is, I think I'm answering to your question, right?
But how does this compare? Let's say we hear 7.5 Richter scale, 8 Richter scale, and how, when you hear 7.7 moment magnitude, how do they compare?
Yeah, there are 2 types of way of measuring.
A scale of 10 or?
Yeah, it's a logarithmic scale. So when you jump from 6.227, it's a logarithmic jump, so times 100, okay? Oh, no, times 10, yeah. So this is how we manage this. This number varies from a small number to a big number. So to properly use it, you have to use logarithmic transformation, okay? That reduce the, let's say, the min-max length. This is how we calculate it. And if I'm not mistaken, this is another way to link the seismic moment to the moment. This is a technical thing, okay? Anyway, you see there is a logarithmic scale over there. So here you calculate the energy in unit per meter, Newton per meter. Since this number is very big, you have to transform through a logarithmic transformation to make it smaller, to be more digestible, okay? What we read, 7.7, is in this scale, MW, okay? But the real energy itself, pure number, should be measured in Newton per meter. But Newton per meter are not really digestible, okay? So we transform into a logarithmic scale, so small number, more easy, even scientifically, to manage, okay? A comparison between the Myanmar earthquake and the Hiroshima atomic bomb, very big difference. So you can imagine, compared to the first atomic bomb in Hiroshima is much, much more bigger. This is power 27, and this is power 4. So order of magnitude 20. It's a huge energy released by this earthquake, okay? So this is energy release, okay? Yeah, it's a lot. It's not comparable.
If there are no more questions, then I would like to bring the event to a close, but Dr. Virdis can talk to anybody who would like to come here and share some comments with him. Dr. Virdis, thank you very much. We have learned so much from you today, and thank you for creating this PowerPoint, especially for the SAM Society. Very much appreciated. Thank you.